Hi guys, welcome to our channel of Sciences and Mathematics. Today we are going to look at the concept and energy changes in physical and chemical processes, and that is the concept of endothermic and exothermic reactions. Now, some chemical reactions involve maybe the release of heat in some form of energy in form of heat, or maybe taking the heat from the surroundings to the system. And we're going to use some of the examples to do our illustration for that, so that you can be able to they basically define this specific concept of exothermic and endothermic reaction. So thank you and welcome. So in this case, we're going to look at an additional concept apart from the introduction to energy changes in physical and chemical processes that we had already discussed in our introduction on the same topic. So we're going to use some of the illustrations that I've mentioned in order to discuss and understand this concept of endothermic and exothermic reactions, and how we can be able to graphically represent them using energy level diagrams. Now I've drawn three illustrations on the board to try and see the effect of maybe dissolving these three sets of substances inside water. And in this case, of course, our main point of interest is to try to see the changes in energy in form of heat. And we're going to measure this using the temperature in order to find the specific change in temperature. But alternatively, if we had an experimental setup for this, and just to give a general demonstration for this, suppose we have a beaker of water and maybe a stand like that. So this is water. Sorry for that. And then maybe we take a spatula full of a substance and dissolve it inside the water. And then we stir it. So we start this one using a glass rod. So this is a stirring rod. So this is a stirring rod. If we stir this specific content for this substance which we have dissolved, perhaps it is, let's say this is ammonium nitrate. We stir it using this glass rod to ensure that it dissolves, and then we place the palm of our hands on this specific beaker. We'll note that there will be a cold feeling on the surface of this specific beaker. So whenever this kind of a reaction is taking place, of course, we say that whenever we are trying to illustrate a chemical reaction, we can draw a dimension, or maybe just a boundary upon which that chemical reaction is taking place, and we refer to this one as a system. And then the junction between this system and the outside environment is known as the boundary. And then this outside environment, which is away from this confined space, which is referring to as a system, is known as the surrounding. So therefore, in trying to illustrate the concept of heat, or the feeling of a cold surface on this case, you find that whenever this reaction is taking place, there's a drop in temperature. The initial temperature was recorded to be 33 degrees centigrade, and the final temperature after some time, when the substance has fully dissolved, was recorded to be 20. So basically there's a change of temperature of negative 13 degrees centigrade, and therefore we are going to see that this kind of a reaction is going to entail taking away heat from the surrounding into the system, and therefore this results in the formation, or maybe the cold feeling of due to a drop in temperature. Now suppose we had this experiment using a different maybe set of a substance like sodium hydroxide. So I'm going to just do this for demonstration purposes. So this is sodium hydroxide. We're going to see that the difference between the initial and the final temperature is an increase. So therefore, I can just be able to illustrate this. So for the first experiment, there was a decrease in temperature. The second one, there's going to be a warm feeling whenever we are dissolving sodium hydroxide until all the crystals may be dissolved, all the salt dissolved in water by stirring. So therefore, for the second case, we are going to see that heat is dissipated from the system to the surrounding, therefore making that a warm feeling on the palm of our hands whenever we are trying to hold the speaker after the reaction. So that one entails the dissipation of heat from the system to the surrounding, and that, of course, is going to entail a reverse concept of what we've already discussed. So the difference between the first and the second kind of maybe experiment that we have to perform for dissolving the two, that is sodium hydroxide and ammonium nitrate, has two particular ways in which we are going to describe them. So in this case, for the first set, whereby we had whereby we had a heat being taken into the system, this is referred to as an endothermic reaction. And for the second one, whereby there's an increase in temperature that results in the warm feeling, implying that heat is being dissipated from the system to the surrounding, or being lost from the system to the surrounding, resulting increase in temperature that will result in the warm feeling, is known as exothermic reaction. So basically, the dissolution or maybe dissolving of sodium hydroxide in water involves an exothermic reaction, while dissolving ammonium nitrate in water results in the reaction that we call endothermic reaction. So basically, we can be able to define the two sets of reactions or scenarios that I've described on the board, whereby we can say that an endothermic reaction is a reaction which takes place, which takes heat from the surrounding into the system. And conversely, an exothermic reaction is a reaction which heat is produced and from the system and released into the surrounding. Now, these two specific illustrations can be, of course, demonstrated using different ways. And we're going to see that one of the ways in which we can be able to represent these specific happenings is by the use of energy level diagrams. So I'm going to use one of them here so that we can be able to relate. So therefore, if we have a graph of energy against the progress, so we have in this coordinates system, this is a graph of energy. Energy is measured in joules, so maybe we can be able to still to refer to it as kilojoules. That is 10 to power 3, and this is the progress of that reaction. So in some literature, we can find this specific variable referred to as either reaction path, progress, or maybe the route. So it is a reaction path, progress, or the route for that specific variable. So in this case, for the first one, that we are seeing that heat is taken into the system by the decrease in temperature in the surrounding, we can be able to illustrate that one using the energy level diagrams that I've illustrated on the board. So therefore, whenever reaction is taking place, we have reactants which are reacting to form product. So therefore, in this case, we are going to have so there's an increase in energy in that direction as the reaction progresses in that specific direction. So initially, we see that for the case of our reactants, their energy before the reaction will be at that specific point, but after the reaction, decrease in temperature implies that there's the taking in of heat energy from the surrounding into the system. So therefore, there will be a net increase in energy that is reflected by this. Of course, we're going to use it, give it a different denotation. but I've just given it as change in energy delta E as such. We're going to use a different one, so this is just for illustration purposes. So therefore that one results in the formation of products, which we can be able to illustrate as such. So this one we can use an arrow to indicate the direction of that change in energy. So therefore this delta E will imply energy taken in. Now for the energy taken in, as we said, this is referred to as an endothermic reaction. So this is how we can be able to use an energy level diagram to illustrate a reaction that is taking place that entails the concept of taking in energy. And suppose we have the one that is losing energy from the system to the surrounding, then we're going to use a different set of graph, which basically is going to form the opposite of the one we have illustrated. So therefore we'll find that the energy for the reactant will be higher than the energy for the product, which implies basically that the product will have lost energy, so negative delta negative E. So this is energy, I can call it energy lost, or maybe energy is just converted into another form due to the law of conservation of energy. So therefore this is going to energy given out. That's an appropriate term for that case. So this is energy given out. So this kind of a reaction whereby the energy is given out, we call this one an exothermic reaction. Therefore, we can be able to represent an exothermic reaction using that energy level diagram that I've illustrated on the board. So one of the examples of an exothermic reaction is this one, whereby there was an increase in temperature that we can be able to illustrate using that specific case. So in this case, you can see that I've written the reactants and the product, but basically we can be able to represent using the specific reactants that we are trying to use in order to illustrate that energy level diagram. So basically these energy level diagrams are illustrations that show the relative energies of products and reactants. And for instance, for the potassium nitrate, this one, and the sodium hydroxide that I've written on the board, we can be able to illustrate the energy level diagram using this specific example that I'm going to illustrate on the board. So this is the reaction path, and that is against energy in kilojoules. So this is we have potassium nitrate. This of course was losing temperature, so therefore it's an exothermic reaction, and we're going to have it solid dissolved in water, liquid, taking away heat from the surrounding to the system to form potassium nitrate aqueous. So therefore the delta, so we're going to illustrate this change in heat using delta H, which is going to be a positive value as illustrated by the positive trend along that energy in kilojoules variable. So this case for ammonium nitrate, which resulted in the dissipation of heat, we can as well use a energy level diagram to illustrate how that one can be shown. So therefore you'll find that the energy for the reactants is more than the energy for the product. So that is ammonium nitrate. No, it's ammonium nitrate. Basically, this is sodium hydroxide that we're trying to dissolve. So sodium hydroxide is dissolved in water. And then we're going to have sodium hydroxide aqueous. So this basically is very important because it implies the change of phase, or maybe changing of the state of that, the three phase for solids, liquids. Then aqueous solution is basically a substance that is dissolved in water. So in this case, we are going to have a delta heat which has been taken away from the system to the surrounding. Therefore, that's an exothermic reaction, and it's going to be shown using the energy level diagram that I've illustrated on the board. So basically, these are some of the ways in which we can be able to illustrate the changes in temperature, or maybe performing simple experiments to illustrate how we can be able to define or maybe illustrate the exothermic and the endothermic reactions. Now, essence for us is that description that we talked about, how we can be able to describe the nature of a reaction, whether it is exothermic or endothermic, by trying to feel the temperature maybe of the beaker for reactions which are performed in this scale that we've talked about, or maybe by using a thermometer instead of a glass. So instead we use a glass rod for stirring, but we can do a substitution for the thermometer, whereby we dissolve sodium hydroxide inside water, and then we start using a thermometer gently until all the solid is dissolved, and then we take the initial temperature and the final temperature during the process. And now the change in temperature is going to be illustrated whether it is positive or negative, and then we are going to determine whether the process is either exothermic or endothermic. So basically that is what the two concepts entails, and we're going to see that there are going to be additional information maybe on this kind of reactions, whereby we are required to write a stoichiometric equation for this part of a reaction that is taking place, and there's a temperature that is going to be involved, which is delta H, that specific point with those particular signs for positive and negatives, which are going to illustrate whether the reaction is exothermic or endothermic. But that's a discussion for another day. And now for this one, I hope that whenever you come across a reaction which has got a notation for the negative or positive sign, we can be able to illustrate whether it's or maybe we can be able to say whether it's an exothermic or endothermic reaction, and be able to represent it using the energy level diagram appropriately. So that is it for today, guys. By God bless.